There we go. Folks who are sorry to I'm just going to barge in and be loud and
Please.
obnoxious. Folks who are unwilling to be on the recording, um, feel free to close your video so that you don't turn up. You can just hide off in the corner. Thank you so much, Peter, for agreeing to do this for us. I am
Thank you for
super
having me.
excited that you're here. It makes me very, very happy. And now I think we've mostly got folks moved over. I'm going to assume that we do. I'm going to let you get started. I'm going to stop interrupting.
We all set?
I think so. I'll
Okay.
let you do your own introduction because you're probably better at it than I am.
Okay. I'm so happy to be here. I'm Peter. Um, I guess I've been called a color theorist. I'm not going to call myself that. I'm obsessed with color theory and have spent the last couple years really deep diving on that topic. And part of that has been trying to understand the history of color theory, which is why I'm here today. I teach art and design at a small private school in New Jersey. I make online content. I'm on TikTok as colored.nerd. I'm on Instagram as Art Pete Repeat. If you search up color theory, you'll probably find me. And I've had a blast over the last couple of years connecting with folks online in the realm of color and color theory. I'm a member of the International Society. No, what's it called? I'm a member of something, the Inter-Society Color Council. And I'm also involved with a group called the Color Literacy Project, which I encourage you to check out if you're interested in that. So anyway, my purpose in life right now is educating folks about color theory and the history of why it's taught the way it is. And that's what we're going to get into today. We're going to get into color and the cosmic order, which is my very ambitious title for a talk about color theories in medieval and early modern Europe. We're going to cover the period from about the 12th century to about the 17th century. Okay, so this word cosmic in my title I chose carefully. To the medieval or early modern mind, cosmos was all of creation. It wasn't just a synonym for universe. It actually implied something about structure and order in the universe. They lived in a universe very different from ours, one that was built, right? Not one that was random and chaotic like the modern universe. So this overall sense of cosmic order is the lens I want to use to examine color theory before and up to Isaac Newton. My hope is that you, as enthusiasts for pre-modern times, as people interested in the ways that pre-modern people thought about and used color, for you, this talk will give you some new insights. And so we're going to see if we can answer some big questions, like how are music, color, divinity, and the motion of the planets related? Because in the medieval and early modern mind, they absolutely are.
Did you get okay? Figure out how to move okay, Judy?
Okay, we're going to just remind everyone to mute their machines. Thank you, thank you. All right, so here's the plan. First, we'll take
Callie, get off the couch.
First, we'll take a look at how a comment by Aristotle about ratios set off a whole philosophical tradition of ordering colors based on harmonic ratios. Because if harmonic ratios were good enough for musical notes and heavenly bodies, by gum, they were good enough for colors. Next, we'll take a look at how metaphysical cosmic order, religious cosmic order, influenced the medieval experience of color, particularly as it relates to stained glass. And finally, we'll examine how artists conceived of pigment mixing in medieval and early modern times up to the 1600s, when the theory that all hues could be mixed from red, yellow, and blue suddenly emerged. So as a coda to all of that, I'll end with some comments on how all of those threads converge on Isaac Newton, whose division of the spectrum and arrangement of the color wheel are often misunderstood. All right, so let's go into section 1, color as ratio. So this is a linear color scale that comes straight out of Aristotle, out of antiquity, and echoes all throughout this period. In that text of Sense and Sensibility, Aristotle proposes that all colors are mixtures of light and darkness in different proportions. They can therefore be ordered in a line based on how much light or darkness they contain. So he puts yellow next to white because it contains a lot of white in his thinking. Blue is next to black because it contains a lot of black, and so on. You can see they're not in spectral order if you know Roy G. Biv. This is not Roy G. Biv. It's also kind of influenced by the fact that ancient Greeks didn't really use hue, right? What color is it? Red, yellow, green. They didn't really use hue to organize color the way we organize color in modern thinking, which you may or may not be aware of. So let's look at a relevant passage as well. He offers a few different hypotheses for how colors are generated through mixture. He says, we may suppose that of this plurality of colors, many are the result of a numerical ratio. For the black and white may be juxtaposed in the ratio of 3:2 or of 3:4, or in ratios expressible by other numbers, while some may be juxtaposed according to no numerically expressible ratio, I guess like an irrational number. Well, but according to some relation of excess or defect in which the black and white involved would be incommensurable quantities. And accordingly, we may regard all these colors as analogous to the sounds that enter into music, and suppose that those involving simple numerical ratios, like the concords in music, may be those generally regarded as the most agreeable. So this idea that concords in music involve simple numerical ratios is, of course, not Aristotle's idea. That comes from Pythagoras, right? He studied how the length of a plucked string relates to the pitch of the note it played, and from there developed the idea that harmonious notes are notes with simple ratios. And a quick side note, I know like Pythagoras didn't invent that. There's a lot of historical debate about it went all the way back to Mesopotamia, but to medieval and Renaissance thinkers, Pythagoras invented it. So we'll go with that. Pythagoras developed a scale built on these simple numerical ratios called the Pythagorean scale. And what's wild is that from there, he also proposed the cosmos itself must resonate with the same ratios. Before we get cosmic, let's establish the basics of Pythagorean tuning, if you're not familiar. In modern music theory, we have terms like octave, perfect fifth, whole step, half step. Those all had not evolved yet in the medieval and early modern period. Instead, they're using a lot of Greek terms, so we'll look at some of those. Diapason, I don't know if I'm pronouncing these right, is the octave. Diapente is the fifth. Diatessaron is the fourth. And there are a bunch of other great words like slambinamamenos, which I can't say, and every time I say it just comes out like a Muppet song. But anyway, there are all these Greek terms that are being used through the Renaissance. If you generate a 12-tone scale from these ratios, you get something that sounds a little different from what we're used to in modern times. The spaces between the notes will actually vary some more than others. So they'll have a little stank on them, right? And you don't really notice the difference within the octave. It doesn't really matter. It works fine. But as soon as you start going for multiple octaves, things slip out of alignment. And so here's that. This musical gap in the Pythagorean scale is called a syntonic comma, or a schismus. It has the ratio of 81 to 80. And remember, small numbers and ratios good, big numbers and ratios bad in this line of thinking. So it sounds dissonant. A major project of music theory in the Renaissance was to find a way around it, or to propose a better system. In other words, it really bothered them a lot. But questions about musical intervals, we mustn't forget, were wrapped up with questions about the structure of the cosmos. You may have heard the phrase, the music of the spheres, or the celestial music. Oh, my lights just came on when I said that. You may have heard the phrase, the music of the spheres, but it wasn't literal music. The concept has more to do with the way the numbers worked, or the ratios worked. Harmony was ratio. So the fact that the ratios, like these ratios here, don't but almost sort of add up nice and neat, that's what drove them crazy, these theorists in the Middle Ages. The fact that these ratios could be found elsewhere in nature, including the motion of the stars and the planets, that meant that math could elegantly describe the universe. And that's what drove them sane. Okay, so let's go to Kepler. In 1596, he published The Cosmographic Mystery, defending Copernicus's theory of a heliocentric cosmos, right? The sun is in the center. We're reorganizing things. This did not go over well, as you may know. Kepler decided that the ratios of the orbits of the 6 known planets could be described by a series of nesting spheres and Platonic solids, illustrated here. This is the work of a guy who really, really wanted it all to add up, right? In 1610, Galileo observed the 4 biggest moons of Jupiter with a homemade telescope. That kind of messed with his whole map of the universe, right? We've got things orbiting other things. That doesn't make sense. Galileo saw these moons orbiting a planet, not the Earth, not the sun. So you'd think that that would mean that now the universe was going out of tune. This whole idea of the music of the spheres doesn't make sense anymore. But the truth is always weirder, because here's what Galileo noticed. Those moons that he discovered in orbit around Jupiter, they have orbital periods that resonate with really tidy ratios. So for every 1 revolution that Ganymede makes, Europa makes 2, and Io makes 4. Exactly. So even into the 17th century, these harmonic ratios still seem to be a part of the fabric of the universe. It was still a valid idea. Maps of the cosmos comparing the heavenly spheres to specific musical intervals didn't go out of style. Here's a quick selection. Here's from 1496. You see things like the musical modes. You see tonus, semitonium, right? It's talking about a scale here, and it's relating that to the different spheres, celestial spheres. Here is Flood, Robert Flood in 1617. Really interesting character. But you can see he's got all of these different musical Pythagorean intervals structuring the distances between the spheres in the heavens. And I don't know if you can see that up top, but that's God's hand tuning the tuning peg of like this string that's the universe. Okay. And then here is a really neat geometrical version of that idea by Stanley and Henry Stanley, I think, in 1656. You can see the octave, you can see the diapente or the 5th, you can see the diatessaron or the 4th stacked on top of that, and then you can see I think that's a major 3rd. So anyway, really popular idea throughout this whole period. So then, did the same ratio-based concept of harmony and cosmic order explain color? Seems like a random question now, but at the time, totally not a random question. It was a burning question that a number of philosophers took up. So let's look at Mainetti, an Italian in 1555, who connected his knowledge of music with his knowledge of fabric dyeing. He proposed a color scale based on the Pythagorean music scale. He was inspired by Aristotle's of sense and the sensible, and he wanted to formalize ideas about colors being different harmonic ratios of light and dark, right? So like Aristotle was sort of guessing and throwing it out there kind of thing, and Mainetti was like, no, I think I got it. This is it. Here's his scale. He changes the order of hues from Aristotle, which is interesting. He puts green in the middle, and his reasoning was green is natural. It's balanced, so it's got to be equal parts white and black. Then the other colors, you've got yellow, blue, red, and purple, all in his scheme represented as these different basic Pythagorean ratios, right? Yellow is an octave, blue is a perfect 5th, and so on, okay? I'm not really sure how this all makes sense, but it made sense to him, right? And so he was thinking in terms of the Pythagorean ratios lending order to the cosmos, but he wasn't using the ratios to develop a series of intervals between colors. In other words, this is not a musical scale in his thinking. So he didn't figure that out. But another guy, Mocenigo, did. Mocenigo was a fanboy of Gioseffo Zarlino. Zarlino published Institutioni Harmonicae in 1558, an Italian treatise on music theory. In that, he was trying to solve this big problem, this idea that it doesn't all add up, right? He added to the set of Pythagorean ratios, which previously they were only ratios built on the numbers 1, 2, 3, and 4. We don't see it here, but 4/3 was also included, and that's the perfect 4th. So Zarlino added a couple to that. Let me see here. He added the ditone and the semi-ditone. We would call those the major third and the minor third. He said these are also consonances. These are also harmonic. Don't worry, you can use them, right? So he's saying that we've got more options for harmony. Mocenigo thought Zarlino's system was so beautiful and orderly that it couldn't possibly just apply to music. Here it is. Look how beautiful and orderly, right? So this is Zarlino's diagram of all these different spans overlapping, showing these slightly different major tone, minor tone, semitone intervals that are built on his scale. It's so beautiful that it can't just apply to music. So Mocenigo built a color theory around it and published in 1581. Let's overlay it on Zarlino's scale here, okay? So white and black are at either end of the linear scale, and he gave them the interval of the octave. Diapason is the octave, right? And then yellow and red are spaced as a fifth. And here is Eileen Reeves' translation of the rest of his scheme. She says, the three intermediate colors, which are in fact simple, but bordered by white and black, are red, which is closer to black than white, yellow or gold, which is nearer to white, and hyacinth. He doesn't call it blue, he calls it hyacinth. Don't know why. He orders his colors differently from Aristotle. He carefully places them based on Zarlino's intervals. Hyacinth versus red, that's a semi-ditone. Hyacinth versus yellow, that's a ditone. These are new harmonies that were not available in Pythagorean tuning. So just intonation, which is what this system is called, was so beautiful that it inspired Mocenigo to revise color theory in its image. Other writers like Girolamo Cardano and Marin Mersenne, a French guy, in 1627 followed suit and even added the major and minor third. Speaking of Marin Mersenne, here is one of my favorite diagrams from his book Universal Harmony. It's actually a ripoff of the same diagram we saw from Robert Flood on the Metaphysics from a decade earlier. It shows the cosmos as a one-string lute with God's hand on the tuning peg. And the only thing missing from this is the colors, like the colors should be lining up with that scale. Mersenne did talk about colors in his book, Universal Harmony. Mersenne had to wrestle, though, in the early 17th century, early 1600s, he had to wrestle with Kepler and Copernicus, right? Now the sun's at the middle of the cosmos, not the Earth. We've got elliptical orbits, not spheres. And worst of all, observations of celestial distances that were not harmonic, right? So Kepler's got all these tables of numbers, and Mersenne looks at them really closely. He looks at Kepler and goes on for pages and pages in his book about, like, can I make this work? Is there harmony? Are there basic Pythagorean intervals in Kepler's observations? But there weren't. So he turned his attention instead to music. He basically decided the universe is out of tune, so maybe I have to fix music theory, which is fun. So one of his ideas to try to do that was to find smaller intervals and see if he could build larger intervals out of them more systematically so that they both sounded good and added up. Mersenne developed a system of dividing the octave into 53 equal portions and then built those portions into larger chunks to create different types of semitones, minor tones, and major tones. Descartes, who was buddies with Mersenne, I think Mersenne was like his agent or something like that, Descartes was also working on this problem. Mersenne had been thinking about musical intervals as divisions of a lute string, like this in this picture, as a line, but Descartes did this. He put it in a circle. Descartes abstracted the idea a step further, and he said, let's look at it as a circle diagram so I can kind of look at the intervals and how they line up in a more periodic way. I don't know if this diagram looks familiar to you, but for me as a color theory nerd, when I saw this, all the alarm bells went off in my head because this is Newton's color circle, right? So like, did Newton just steal it from Descartes? Not really, but here's where it gets interesting. A lot of people don't know this, but Isaac Newton actually went on a total music theory bender in like 1665. That was just a few months before he got his hands on a prism. And someday maybe I'll get around to like writing a whole research paper on this, but the gist is this: Newton's hue circle right here is a direct result of him applying music theory thinking to the problem of color. He got his musical scale to add up almost perfectly, right? He was working on this for a couple months, and he started dividing the octave into smaller and smaller chunks. He started building his tones and semitones out of smaller divisions, and he even got to the point where he divided the octave into 53 equal portions. Sound familiar? Remember, Mersenne did that just a generation before. So I think that's interesting. Much has been made of Newton's use of the musical scale to divide the spectrum. Here's his division of the spectrum. It's actually going red on, I don't know my left from right, red on the right to violet on the left. And this diagram is from his optics. So if you look at the ratios along the bottom, those ratios are not Pythagorean ratios. We've got 8/9. We've got 9/16 in there. I think so. My thesis, I guess, here is that it's I'm losing my place in my spot in my paper. Sorry. He got into color and light just a couple months after this 53 division of the octave thing was obsessing him. So he went into color theory with the ratios of music very much on his mind, and he didn't take Pythagorean ratios for granted, right? He wasn't like, yeah, that's what we've been using for centuries, I'll just go with that. He must have considered many options for his division of the spectrum before settling on and choosing the ratios here, which were the ones favored by Descartes. So in a way, he was setting out to solve the same problem as Mersenne and Cardano and Mocenigo and all these other guys. And in the end, he wasn't satisfied. In the optics, he actually criticizes his own color wheel and says, this rule, meaning the system I've come up with, I conceive accurate enough for practice, though not mathematically accurate. Okay, so we're going to move on to a new topic here, and then hopefully all these threads will tie together at the end. All right, we're going to now look at color as divine splendor in the Middle Ages. Okay, so it's fair to say that most of your everyday artisans and illuminators and painters and dyers in this time period were not reading all of this philosophical literature on color, but they were going to church. So I want to take a quick detour into the more religious side of color theory. All right, so this is the Abbey of Saint-Denis. It's now a basilica. In the 12th century, a guy named Abbot Suger was in charge, and he was kind of a big deal. His program of renovations for this abbey near Paris basically kicked off the Gothic architecture style. He kind of took all of these elements that were floating around and put them together, and that became the Gothic movement in architecture. So here is an engraving that he had engraved into the choir of the abbey in 1144. Because the new part, the part I just built here, rejoins the anterior, the room lit in its center gleams, because what blends with the very clear clarity, and because a new light traverses it, the noble work shines forth. So the word for light he uses is lux, and that's important for a very specific reason. This noble light that he's talking about shining forth, this lux nova, I think it's pretty important that it was multicolored light coming through these stained glass windows. Suger believed that light was divine. It emanated from God, but he also believed color in the form of colored glass and precious stones would elevate worshippers' experience in the abbey. Why did he believe that? Okay, so based on St. Bonaventure's theory of light, Abbot Suger believed this. He believed that there were three parts to light. There was lux, which was the light itself, the light source, I guess you could say. There was lumen, which was the part that could be said to be carried through space by a transparent medium, the rays themselves. And then there was splendor, which was the reflection of light by opaque bodies. This is where color fits in. It's a form of splendor. So I'm going to actually attempt, if I can unshare for a moment, to illustrate this. Okay. if you can see me here, I've got a blank wall and I've got a little piece of, we'll call it stained glass, a little filter. What I'm going to do is I'm actually going to shut off my room lights for a second. And I'm going to let the divine light of my light here shine through my stained glass window and land on my wall. Okay, so what we have here is the three components. You can't see my light source because it's God and you can't see God. Your puny human brain can't comprehend the splendor that is God's divine light. But you can detect the presence of it through lumen. You can't see the lumen either. The lumen is like here, right? You can't see it because you're not looking right at it, but trust me, it's passing this way through this filter to hit the wall. So that's lumen, and then the part you can see with your puny human brain is what's falling on the wall, and it's been colored by the glass. That is the splendor. So color is seen as this way to make light corporeal, a way to make light something that we in the human realm can experience. And all the different flavors or shades of color are just evidence of all the different ways that our human perspective kind of colors and corrupts the divine light of truth. Okay, so we've got here like a color theory that's very much metaphysical. Okay, I'm going to go back to my my slides here. Bear with me one moment. Okay, good. So just catching up to my notes. Okay, so the scholar Alberto Virdis talks a lot about how color was very ambiguous to medieval thinkers in the sense that it wasn't clearly light and it wasn't clearly matter, but it somehow belonged to both realms. Color is like the intersection between light and matter, and therefore between God, divinity, and the human sphere, right? So it's this ambiguity of color, this weird in-betweeniness, right? That, I think, is key to understanding Suget's medieval attitude toward color and its function in a sacred space. It could aid in devotion. It could bring worshipers closer to God by making the cathedral a place where matter and light could blend together. So to sum all of that up, Suget is a kind of a juncture point in medieval color theory. His interpretation of Neoplatonic and Christian writers on optics, light, and metaphysics influenced the way medieval European Christians experienced color and light for centuries. They experienced it in these sacred spaces as the effect of divine light made manifest, of the invisible made visible through coloration. This religious context for understanding color was still certainly present to some degree through the early modern period and even in Newton's 17th century world. So for him to propose that white light could be produced by mixing together different colored rays, that turned everything on its head. It meant that color was not a modification or a corruption of divine light through degradation that comes from contact with the physical world. It meant that color was something else entirely. And that was kind of a dangerous and scary idea. That was like Darwin level scary for the time. Okay, but we'll come back to that at the end. I want to get now into color mixing and be mindful of time. Here we go. We're good, I think. All right. So let's start in a kind of an unlikely place. We're going to go back to Aristotle, but we're going to go to a treatise on the weather. So his book Meteorology has all these descriptions and scientific discussions of optical phenomena in the atmosphere, including rainbows. So here is his description of rainbows. Each bow of a double rainbow is 3-colored. So he's not like Newton saying, Roy G. Biv, there's 7 colors of the rainbow. That's what we learn in modern times. He's saying the bow of the rainbow has 3 colors. The colors are the same in both bows. The outer rainbow, they are fainter, their position is reversed. In the inner rainbow, the first and largest band is red. In the outer rainbow, that band is nearest to this one and smallest. It's of the same color. The other bands correspond on the same principle. These are almost the only colors which painters cannot manufacture, for there are colors which they create by mixing, but No mixing will give red, green, and purple. Isn't that very interesting how he says that? He defines the principal colors of the rainbow in relation to artists' paints, saying the red, green, and purple of the rainbow can't be mixed by painters. So like as a modern person, we recognize this way of defining primary colors as colors which can't be mixed on the palette. That's kind of what we're taught in school, right? But few of us would choose the hues red, green, and purple as the unmixable ones. We'd probably say red, yellow, blue. Our framework for primary colors that says red, yellow, blue actually comes from a theory that emerged around 1600, and that's what we're going to get to here, okay? So while meteorology is not a treatise on paint mixing or color theory for artists, Aristotle's roping in paint mixing in his discussion of rainbows, and that has an impact on how later theorists frame color mixing for artists. Why? Because other classical texts, including Aristotle's Of Sense and the Sensible, only treat black and white as the simple or primary colors, from which all other colors are mixed. Here, in the meteorology, he discusses the rainbow as having three primary hues: red, green, purple, which today we might recognize as RGB, or the pixels on your computer screen. In fact, our modern term primary color comes from the meteorology. Oh, I forgot to show you this. Here it is. Here's his double rainbow diagram. One thing to note here is actually flavus, or yellow, is in there, but it's on the line, if you can see that, between viridis and punicius. He's using phoenikios in Greek, which is really kind of more like magenta to describe red. I could go on for an hour about that. It's very interesting, but I won't. Anyway, let's move on. So up top, you see from a Latin translation of the meteorology. Basically, we've got this term colores, I can't see because of the zoom stuff, but I think it's iridis, meaning of the rainbow, colores iridis primarii. So the primary colors of the rainbow. So colores primary, or primary colores in Latin, is where this term primary colors comes from. Okay. The first mention of it that I've found in English is in a lapidary, a book about gems and stones, by a guy named Nichols. And you can see he uses the Latin spelling, primarii colores, but he's using it to define what we would define it as, colors which arise not from the commixtion of other colors. And then he lists white, black, blue, or sky color, yellow, red, miniatus color, which is minium, or vermilion, or fiery red. So it's interesting, he gives us two versions of red. Again, I could go on for an hour about that, but basically artists have always known that red and blue, like fiery red, vermilion red, and blue, don't really make purple. And I think there's a class later about that, so I won't steal the thunder. Anyway, the first actual English rendering of the term primary colors that I have found is Robert Boyle in his book, Experiments and Considerations Touching Colors, in 1664. And here you see it. He says, there are but few simple and primary colors, if I may so call them. So he's kind of like taking credit for coining the term primary colors, if I can call them that. So there you go. He says later something similar to Nichols. He says like painters can use 5, but he only includes one red. He says red, yellow, blue, black, white. We'll get to that again later. All right, so let's back up a bit, because before we get to the 17th century, when we're back in the medieval period, we don't have any of this red, yellow, blue stuff. Okay, so medieval artists up to about the 1400s strongly preferred to work, excuse me, in fully saturated colors. Like stained glass artists, they could model forms by just adding some black to the color. Or in the Florentine tradition, which is what we're seeing here on the slide, they would just use the fully saturated color as the shadow. Like you can see the blue in those robes. In the shadows is not dark and shadowy, it's just as blue as it can get. And they would model the highlights with white. This practice was actually influenced by Cennino Cennini's manual on painting. He really only encouraged painters to modify the given hues of their pigments in terms of lightening them. And when it came to mixing pigments of different hues together, like red and blue to make purple, he actually didn't advise painters to do that at all. There were practical reasons behind that hesitation. Many of the pigments in use in the medieval and early modern periods were not mixture friendly. Minium, or more specifically orange tetroxide of lead, was liable to tarnish. Mixing it with other pigments made it more susceptible to discoloration, because if you're mixing a pigment, you're actually thinning it out, and you are making more of its surface area available for chemical reaction. Azurite, another example, that's a copper-based mineral that gradually shifts from blue to green if it's exposed to humidity. If you glazed it too thin and left it exposed to moisture, it would turn green. And that's actually where the green pigment viridian comes from. Then there's orpiment. Orpiment is a toxic yellow pigment that was widely used by medieval illuminators, but it reacts with red lead, lead white, and verdigris. So while you could mix orpiment with indigo and get a green called virgo, you couldn't mix it with a bright red like minium to get orange. It wouldn't work. So that kind of precludes you in the medieval period from inventing a color circle. It wasn't just chemical reactions holding artists back from mixing hues. It was the media they were painting with as well. Some of you, I'm sure, have worked with egg tempera or glare, and you know that it dries very quickly. It doesn't make sense to mix different colored paints if they're going to be dry before you can arrive at the color you're trying to get. Neither is fresco a friendly medium for hue blending. I mean, like, you could get there after years and years of practice, but it's just like the results you're going to get are not going to be consistent. And so this idea of creating new colors by physically blending pigments together was generally avoided in the medieval period. There were various recipes for mixing pigments of different hues, like Virgo, that green. But none of the mixing that was going on had anything to do with a systemized dimension of hue. This way of thinking that we take for granted of saying, how do I get orange? Oh, I'll just mix red and yellow. How do I desaturate green? I'll add a complementary color. That way of thinking about color mixture is entirely modern. Okay? So the carefully learned caveats about pigments and how they interact chemically and all that, that meant that there was no real agreed upon map of hue in the practical arts. There were only the abstract philosophies of harmonic ratios of light and dark we've discussed, and as we noticed, the color order was changing with each different author because, like, they weren't going based on the spectrum. And so those philosophical schemes of hue were not of any use to painters or dyers. However, things did start to change as we transitioned to the Renaissance, and a key reason is the rise of oil as a painting medium. So let's take a look at the Arnolfini Wedding by Van Eyck. So Shapiro and other scholars have noted that the palette, the tool of the palette, didn't actually emerge until around 1400. A palette's no use to a fresco or a tempera painter, really. So it wasn't until the rise of oil as a medium that mixing on the palette as you go was practical. Paints that stay wet long enough to experiment, to see what happens when you mix them together and have it not be super costly. That was a game changer, right? So now that there was room to do that, that's what artists did between 1400 and 1600. Gradually, more and more artists and authorities on color mixing questioned this Aristotelian color line. Alberti, in 1435, his book was published later, but he was writing in 1435. He seems to be among the first to suggest a limited number of chromatic primaries. In other words, not black and white, but different hues, chromatic primaries, could be used to mix a full range of hues. So we don't really have a diagram from him. This is a modern reconstruction of his thinking, but he's got white up top, black down at the bottom. All those lines going up and down are like shades and tints of colors by adding white and black. And then if you take yellow, green, red, and blue and set them up as four corners, you can see that you can kind of mix all these different hues in between them. So he's really the first guy to start thinking in this way. It wasn't until the turn of the 17th century, though, that writers settled and kind of all agreed at the same time on 3 primary colors for pigment. So the idea sort of like exploded all over Europe at once. Charles Parkhurst has raised the question of why 4 different descriptions of a red, yellow, blue system emerged suddenly, like within years of each other at the same time. So there's Scarmiglione in 1601, there's Francois d'Aiguillon in 1613, Louis Savot in 1609, and then in the Netherlands, Anselm de Boot in 1609 as well. All 4 of these like different authors from different backgrounds are all presenting like within a decade red, yellow, blue mixing theory. Where did it come from, right? Most of their thinking actually seems to have been done in the 1580s, and then there were like publication delays for a number of reasons. And I don't know if you remember this from earlier, but in the 1580s, somebody else was working on this, Monchenigo, right? And he said the 3 intermediate colors are in fact simple. So simple is his word for primary. So really in 1580s is where you get this idea that red, yellow, blue are primary, can be used to mix other hues, and then it kind of becomes accepted and propagated in the first couple of decades of the 1600s. All right, so let's look at d'Aiguillon a little more here. d'Aiguillon seems to be the first to illustrate the idea that some hues were not in the linear sequence at all. So, right, you still got that Aristotelian line of colors down the middle. You've got albus, flavus, rubeus, caeruleus, niger. I don't know Latin. I'm pronouncing them wrong. I'm sorry. But it's white, yellow, red, blue, black. And then on the bottom, he's saying these are not in that line. They're like on another dimension. You've got aureus, gold or orange. You've got purple and you've got green. Let's actually do this so we can see that a little bit better. Okay, so they're sort of, we've got these tangential colors. We've got this other dimension of hue going on instead of conceiving everything as harmonic ratios of white and black. d'Aiguillon was also, it seems, the origin of a particular way of thinking about pigments as imperfect primary colors. He reasoned that minium was not a good a good pigment to mix purple with because it had a little yellow in it. And lake was an okay red, but it had a little blue in it. That way of thinking of a pigment as having different components or amounts of red, yellow, and blue comes from d'Aiguillon. And that actually remains a popular way of thinking about paint mixing today, even though it's sort of pre-scientific. All right, so a last thing about d'Aiguillon was he kind of pish-poshed the whole musical ratios and color ratios thing by saying this. He said, that which is perceived through color has only to do with sight, that which is discerned through sound only with hearing, right? Like, let's not pretend that there's one hammer that hits every nail here. And so he disagreed with Mainetti, Mocenigo, Cardano, all of these other Renaissance authors by saying that. All right, so this system gets a little bit simplified. Kircher, Athanasius Kircher in 1646 gives us this version of that same idea. You could put the colors on it like this. Robert Boyle, as we saw in 1664, he actually, here's the rest of that quote. He writes about white, black, red, blue, and yellow. So he's drawing again from this same new line of thought. Then you've got William Petty, who presents this paper to the Royal Society in 1667. Right around the same time, Newton was doing his experiments with prisms and stuff and was like being a drama queen about it. Petty was like, so here's how dye mixing works. You got blue, yellow, and red. And then you can see he actually recommends some specific dye stuffs like Brazil wood, madder, cochineal, etc. And kind of talks about their various virtues as mixing primaries. Okay. So all of this, as I said, was right around when Newton was working out his theory of light and color, and it actually made it harder for him to be accepted. For him to propose in 1675 that all spectral colors were homogeneal, in other words, were not compounded, but were primary, for him to propose that was not well received. Like, are you kidding me? Orange is primary? Indigo is primary? Are you out of your mind? We can mix those colors. That's what people were saying. All right, so we're coming in for a landing here. we've circled back to Newton at the end of each section because I want to try to tie all of this together with him. All of these different theories of colored light, of colored intervals, of color mixing, they all kind of come to roost in Newton's brain in the 1660s. I want to look at what this color wheel was actually trying to do. Here's what he says in Proposition 6, Problem 2 of the optics. He says, in a mixture of primary colors, the quantity and quality of each being given, to know the color of the compound. That's his proposition. And his answer is this diagram. Here's how I can predict the way two different colored beams of light will mix. I can do it with math, with geometry, all right? Not just geometry, calculus, which you may know he was also inventing at the time. All right, so I'm just going to read now to try to catch up on time for you guys. So we've seen that Newton's circle was a diagram of a musically derived color interval theory. He carefully divided the spectrum according to Descartes' preferred harmonic ratios. Remember, this is the man who wrote the Principia. He deeply believed that mathematics would reveal the secrets of the cosmos. And to that end, this color circle is also a diagram of a color mixing theory. He's thinking about colors as arcs of that circle, as sections of its perimeter, right? He's thinking in terms of calculus. And he's actually using the term primary color to mean a single type of spectral ray, because he didn't have the term wavelength that came later. He used the term primary to co-opt the recently established term that Boyle and Petty and all these other guys were using, to co-opt that term to his own theory. And when he gives an example of how to calculate the mixture of two colors on his diagram, he calculates the line between their centers of gravity. And center of gravity is a key problem of calculus, right? So his circle was meant to illustrate the beautiful calculus he saw in the musical ratios of colors that emerged from the prism. Couldn't those other fools see? Any spectral hue was primary because any could be isolated as a pure color and any two could be mixed in a systematic way, and his hue circle could predict the result. Newton created the circle to prove that, quote, whiteness is a mean between all colors. Whiteness is the average of all colors. In other words, white light is not exactly the divine source of all colors. When mixed with darkness, it doesn't get corrupted. It's the average of all colors. It's the center of the circle because it's the balance of all colors mixed together. Was that sacrilege? I don't think so. In fact, Newton didn't claim that rays of light were colored. Quite the opposite. Let's look at what he said here. He said, for the rays, to speak properly, are not colored. In them, there is nothing else than a certain power and disposition to stir up a sensation of this or that color. So, given the context of the theory of lux, lumen, and splendor, I think we can read that line a little more carefully. Rays of light are lumen, emanating from the divine lux of God, and as such, they possess power to stir up the sensation of colors. The colors then are a byproduct of the interaction of light and subjective sensation, and that's splendor. I think I'll end there. I hope you have questions.
Thank you so much for that, Peter. I can keep an eye out for questions for you, or you can keep an eye out yourself.
That would be great. I see a hand up.
Yeah.
Asleep.
Asleep. Folks are welcome to unmute themselves and just ask, or they're popping into chat, whatever makes you comfortable.
So a couple notes. So I noticed that, so this is kind of slightly off topic, but when you're buying, little bits of paint, you get all of those colors that you noted as your colors in your primary paint kits when you buy them. Like, so when you buy a little bit of like gouache or watercolor, you get white, yellow, 2 colors of yellow, 1 blue, 1 green, 1 black. Like, it's like everything that you noted on those color wheels, we get 1 of each when we're buying those colors as paint. And that's really interesting, like how that kind of keeps transferring forward.
Yeah, yeah. I think most color theory education today is actually still pre-scientific. Um,
hmm
this idea of split primaries or warm and cool primaries
Yep.
is like a modern adaptation of what Daguillon was talking about.
Yep.
I see another hand up from I'm going to say your name wrong. Diava the Weaver.
Yeah, it's Welsh to just mess with you. Um, so I had a question going back to the Middle Ages and perceptions of color. Because you talk a lot about, of course, the painters.
Mhm.
How were dyers and weavers perceiving color differently than painters were because they're using different materials?
Mm-hmm. So the interesting thing with dye, I can't speak in detail about that, but the interesting thing about dye is that it has no particle size, so to speak, right? It dissolves completely in water. And so the way it interacts with water actually changes its refractive properties. And so, you probably know this, the concentration of a dye affects not only its intensity, but also sometimes its hue. So you're going to see things like Brazil wood or madder actually take on a different hue based on its concentration. And dyers would have had to learn that and know that and work with that information, whereas painters would not, right? So I'm thinking of things like, it's going to look more red when it's more concentrated, but it's going to look more magenta when it's thinned out. That's going to happen in a dye more than it is in a medieval paint. As far as weavers, there's a great book, I think it's from the 16th century, uh, The Complete Gentleman. I'll have to find the citation again, but he gives a whole description based on ratios of how to actually, like, how many threads of one color versus another color to lay together in your weave to get optical mixtures of hue. And it actually matters more to that guy how light or dark the color is. Like, you should be doing 1 to 2, where 1 is the darker color and 2 is the lighter color. So weavers were thinking in these terms of ratios as well.
I'm going to throw one thing back at you just to
Mhm.
think about.
Mm-hmm.
Indigo is not water soluble. And so
Okay.
how you achieve shades with indigo is a different process.
Okay.
And the same is true with woad. And we know that alkanet is the same way because it requires metallic salts to be able to dissolve it, and it's not really very water soluble.
That's good to know. Like I said, I'm not a dye expert, so thank you for adding that
Yeah,
correlation.
Diac for the Weaver, what can I say?
Good. I see a hand up from Sancha Lestrange. L'Etrange.
Hi, I just come off a few decades of teaching college art
Mm-hmm.
and teaching art appreciation to students who, in most cases, have never even thought about doing art or about it in any way. Really articulated some of the interesting ways that we take it for granted and don't.
Mm-hmm.
But introducing the color wheel to adults, and then introducing them to paint, and the need to actually explain that the color wheel is a theoretical construct,
Right.
because cheap student paints are pretty close to that. But when you get to real paint with real materials are never the theoretically pure hue. They can come close, like ultramarine.
Right.
But in general, real pigments are never going to match that theoretical construct. And obviously, this didn't hinder actual practitioners, but the reverse never hindered the theorists.
Mhm.
And my point of interest is the interface between them, which I think in period was almost nil. The interesting
yeah.
references in Aristotle that you brought up.
So I think Daguillon is kind of the exception to that because he was buddies with Rubens. Rubens actually cut the frontispiece for his book on optics, and
Mhm.
and the same year it came out, painted this painting with Juno, Iris, and the head of Argus. It's a great painting, which some scholars say is like a celebration of red, yellow, blue theory. So there was, by the 1600s, some contact and kind of exchange of ideas between artists and theorists going on, but not until then. Yes, I see a hand up from Aline.
Yeah, I just was, I came in late because I'm further west and it was farmers market day today. But what I found really fascinating was thinking about your commentary on the fact that glare doesn't stick around. But of course, there were other media. I mean, I'm both a dyer and an illuminator, so I do both of these things. And I use modern gouache, but you could use gum arabic and other such things, which can be re-wetted, and you can, in fact, mix colors. But it was really a kind of an insight to think about how late it became easy to mix colors. So I wanted to thank you for that.
Thank you. Yeah, I was surprised at how late it was too, kind of when doing my research. I assumed when, Boyle was repeating red, yellow, and blue are the primaries, he was repeating something that had been taken for granted by artists and dyers for centuries. I didn't really realize that it was only around as an idea for a few decades at that point. It's really quite fascinating. All right, Philippa.
Yeah. Hi. So I'm actually studied linguistics in college, and I'm not sure if you're familiar with Berlin and Kay and sort of their
Mhm.
theories of basic color terms and languages. And I mean, I don't know that there's a question here, but I think it would be interesting to track sort of like how are the basic color terms within different languages. I know especially like ancient Greek doesn't particularly reference blue, and how does that impact the way people are talking about and conceptualizing these colors when there are categories that don't have their own distinct names.
Yeah, that I could go on for an hour about that, I think. Just a couple quick comments in reference to that. I think in the 1600s, when Newton is formulating his theories, there's actually some interesting things going on which influence his thinking. He actually sort of had a concept of cyan. In his Latin manuscripts, in his letters to the Royal Society, he uses the term cyaneus, but it doesn't make it into the final book. Like it's too out there. And then the other thing is orange. He's actually sitting right on the transition of that becoming a basic color term. In his earlier notebooks, he uses the term orange tawny to describe the color, which was kind of the customary way to describe that for a while. And so it's an adjective, it's not a true color term. But then in his later writings, he shifts to orange. Um, I don't know why. I mean, I think it was just the evolution of the language happening right in front of him. And then indigo is interesting as well because of kind of the economic importance of it to England in that century as well. There may have been some reason for using that term related to that. So yeah, there's all kinds of fascinating push and pull of these what gets to become a basic color term. Um, modern scholars are actually starting to think turquoise is going to count as one because most of these like industrialized countries now have a pretty good agreement on this color between green and blue and a term for it. All right, moving on. TADC. I will not try to pronounce.
It's Tadek. Really excellent talk. I just wanted to make a quick note about orange. My research with dye specifically centers around the Plictho, which is a it's the first professional printed dyer's manual from 1548 from Venice. And he has recipes or formulas for orange, and it's not an orange, it's just orange or a deeper orange. And from my research around where orange pops up specifically in the Italian, or like in Venice and in Italy more broadly, it actually is dated to the century previous as a color, which I thought was really interesting because orange is in kind of a weird spot in terms of when it comes in as a color.
I wonder if that's because the Italians had more mercantile contact with the Middle East, right?
Oh, it's absolutely got a lot to do with that. So, and Rossetti worked for the Arsenal. So,
yeah. Oh, that's interesting. Cool. Asleef has another question.
Sorry, I don't want to I don't want to take too much time. I don't want to but as you were going through and showing all these things, it was sparking things in my brain because so the thing I'm doing later is about uroscopy wheels and the colors of those, and I wondered why they were in that specific order of colors, and it perfectly follows the order of colors that you laid out in the line. And I'm
Mhm,
like,
mhm.
oh my God. So like medicine goes with the color theory, which goes with the whole like, so I'm starting to sort of dive into medieval medicine. And
Yeah,
so this is like giving me all kinds of new avenues to go exploring.
yeah.
This is really, I just
Cool.
wanted to say thank you.
Yeah. I mean, you've probably looked into all the urinalysis stuff, right?
Mhm.
Yeah, Robert Flood was like some actually credit him as having the first color circle and not Newton because he had one for urinalysis. Which is interesting, but it's not a spectral hue circle. It's an
No.
Aristotelian one. Yeah.
Yeah, it follows the colors. And I was like, well, why
Yeah.
did we go from like why is blue in the middle and black on the end and like why is white
Yeah.
first? It's like, whoa. So now I just want to say thank you because now I have like
Sure.
all kinds of new things to kind of dive into. So
Awesome.
thank you.
Well, that was my goal. Good.
Hey.
Cool. I don't know if I've missed any questions that are in the chat. If I
Haven't
haven't,
spotted any
apologize.
more in the chat. We are coming up to lunchtime, so it's okay if we run a little bit into it. We scheduled a lunch break for everybody so that we make sure that everybody gets up and stretches, even if it's breakfast for some of you and supper for others, that everybody actually takes a little bit of time to get up and stretch. I just wanted to jump in here and thank you so much, Peter, for sharing your enthusiasm and your passion and your joy in early color theory. This was absolutely fascinating, and I am a dye person rather than a pigment person, and I now have so many extra rabbit holes to go dive into. And RIP my spare time.
Yep.
I think I speak for everyone in saying thank you so much for sharing with us.
Yep.
Thank
Thank you.
Thank you.
You're welcome to come and hang out with us for the rest of the day. I'm just gonna get the recording shut off because I think we're
Sure thing.